A very good morning, my dear students. In the previous lecture, we have started discussing the different types of counters, that is synchronous counters and asynchronous counters. And in addition to that, we have also seen the what the differences between the synchronous and asynchronous counters, and also we have seen the working of the example of asynchronous counter, that is ripple counter, a 4-bit ripple counter, which will be counting the number of clock pulses up to 16, maximum of 2 to the power of 4. So since it is a 4-bit triple counter, it can count up to maximum of 16 clock pulses, 2 to the power of 4, 0 to 15. So in today's lecture we will mainly concentrate on discussing the ring counter and also its applications. Ring counter will be coming into the category of synchronous counters. So now in the previous lecture we have discussed the example of asynchronous counter, that is 4-bit ripple counter, and in today's lecture we will mainly concentrate on discussing the example of synchronous counter, that is ring counter. So the main objective of this lecture is to know what is meant by ring counter and construction of ring counter, how the ring counter is constructed, and also the working of ring counter based on the diagram, and also we will see the at last the applications of ring counter. In the previous lecture we have seen what is a register. A register is group of flip-flops which are used to store the data. Register is nothing but a group of interconnection of flip-flops mainly used to store the data or shift the data to the left or right, and various manipulations can be done with the data present in the registers. And what is a memory device? Memory is a device that stores information in electrical or magnetic or even optical forms. So this is nothing but memory device. And what is a buffer register? Buffer register is the simplest possible type of register. And at last, what is a counter? In the previous lecture we have seen what is a counter. A counter is a logic circuit or digital circuit which is capable of counting the number of clock pulses that are applied at the input of the counter circuit. So a counter is a logic circuit or digital circuit which is capable of counting the number of clock pulses that arrive at its clock input. So these are all the things we have seen in the previous lectures, and in today's lecture we will mainly concentrate on the ring counter, which is the example of synchronous counter. Synchronous counter in the sense clock input is applied to all the flip-flops at a time simultaneously, whereas in contrary to that, asynchronous counter means clock input is applied only to the first flip-flop, and the clock input for the rest of the flip-flops will be derived from the outputs of previous flip-flops. That is asynchronous. And in the case of synchronous, clock input is applied to all the flip-flops at a time. And the example for synchronous counter is ring counter. So what is ring counter? Instead of counting with binary numbers like starting from 0 to 16, 0 0 0 0 0 0 0 1 0 0 1 0 like that, ring counter uses words that have only a single high bit. For example, if I am considering a 4-bit ring counter, in that 4-bit ring counters you will be getting 4 outputs, and in those 4 outputs only one output becomes high, like 0010 0001 0010, next 0100, next 1000, and again it starts from 0001. Okay, so that is nothing but ring counter. So instead of counting with binary numbers starting from, let us say, we have seen 0000, 0001, 0010, 0011, like that, it is not counting of number of binary numbers. It is the ring counter uses words that have only a single high bit, so that is nothing but ring counter. Ring counter can be constructed either with D flip-flops or JK flip-flops. Even in the earlier class we have seen ripple counter that is also constructed with the help of what, JK flip-flops, or you can also use T flip-flop for toggling. Okay, so any JK flip-flop or T flip-flop are used to construct ripple counter, whereas D or JK flip-flops are used to construct a ring counter. So this is the basic block diagram of a ring counter. I have used D flip-flops here, and to the first flip-flop I am applying preset input, and to the rest of the flip-flops I am applying clear inputs. So these preset and clear inputs are asynchronous inputs for any flip-flop or for any sequential logic circuit. So preset inputs and clear inputs are called asynchronous inputs for any flip-flop or any digital any sequential logic circuit. So here for the first flip-flop I am applying preset input, and for the rest of the flip-flops I am applying clear input, so that initially you are making the output of the first flip-flop as 1. Initially you are making the output of the first flip-flop as 1, and rest of the outputs of all the flip-flops becomes 0. That is the meaning of clearing the rest of the flip-flops and presetting the first flip-flop. So initially the contents of the outputs of each and every flip-flop is like this: 0 0 0 1 before applying any clock pulse. Okay, so this is the significance of asynchronous inputs called preset and clear inputs. So irrespective of the clock available to each and every flip-flop, or irrespective of the inputs available to each and every flip-flops, if preset and clear are applied to the flip-flops, it will be uh, applied accordingly to the circuit. So in addition to that, here the circuit is, why the name ring counter? So see, if you observe the first flip-flop output, it is given as input to the second flip-flop. Similarly, second flip-flop output is given as input to the third flip-flop. Similarly, third flip-flop output is given as input to the fourth flip-flop, and in the similar manner the last flip-flop output is again given as input to the first flip-flop. Last flip-flop output, that is Q3, is again given as input to the first flip-flop, that is D0. So that means this forms a ring-like structure. This forms a ring-like structure between the inputs and outputs of each and every flip-flop. So the first flip-flop output is given as input to the second flip-flop. Similarly, second flip-flop output is given as input to the third flip-flop, and third flip-flop output is given as input to the fourth flip-flop. And in similar manner, in order to complete the ring-like structure, the output of last flip-flop, that is Q3, is given as input to the first flip-flop. And this, as long as you are applying the clock pulses to each and every flip-flop, the outputs will be keep on producing. So for initial setting of the inputs, for the initial setting of the outputs, you are clearing the three flip-flops and you are presetting only the first flip-flop. Okay, so initially the output of first flip-flop is made as 1, and rest of the outputs of the flip-flops will be made as zeros, so that as long as the clock pulses are applied, that single high bit will be transferring from one flip-flop to other and other to other, like that. So this is the basic block diagram of ring counter. I can say this is a 4-bit ring counter. 4-bit ring counter. And even if you observe, in the previous lecture we have seen the 4-bit ripple counter, and since I have considered a 4-bit ripple counter in the previous lecture, by using 4-bit ripple counter you can able to count 16 different outputs. You can able to have 16 different outputs. That means how many maximum number of clock pulses it can count? It can count a maximum of 2 to the power of 4, which is equal to 16. You can count a maximum of 2 to the power of 4, which is equal to 16. So this is the previous one, the asynchronous or 4-bit ripple counter. When it comes to the synchronous ring counter, I am considering now a 4-bit. I am considering now a 4-bit ring counter. By using 4-bit ring counter, how many number of clock pulses it can count? Only 4 clock pulses. It can count only 4 clock pulses. That means only 4 different output states are there. 4 different output states are there. That is the difference between a ripple counter and ring counter. That is the difference between asynchronous counter and synchronous counter. So in the case of n bit, if you observe, a n bit ring counter will be counting only n clock pulses, whereas a n bit ripple counter counts 2 to the power of n number of clock pulses. So that is the difference between ripple counter and ring counter. So n bit ripple counter counts the maximum number of 2 to the power of n number of clock pulses, whereas n bit ring counter only counts n number of clock pulses only. N bit ring counter counts only n number of clock pulses. That is the basic difference between ripple counter and ring counter. Okay, so this is the block diagram of ring counter. Next we will observe working of ring counter. Q0 output sets up the D1 input. So as I told earlier, the Q0 is nothing but the output of first flip flop, which is given as input to the second flip flop. Similarly, Q1 output, which is nothing but output of second flip flop, is given as input to the third flip flop, and so on. Means in the similar manner, the Q2 output, which is nothing but output of third flip flop, will be given as input to the fourth flip flop, that is D3 input. And in the similar manner, the output Q3 uh, Q3 the output of fourth flip flop is given again as input to the first flip flop. Okay, so ring counter resembles a shift left register and rotate left register. Okay, so if you observe in the previous slide, we have seen like this. That means Q0 output is given as input to the first flip flop. First flip flop output is given as input to the second, and second flip flop output is given as input to the third. Third flip flop output is given as input to the fourth, and fourth flip flop output is again given as input to the first flip flop. So that means if you observe the basic structure of circuit diagram of ring counter, it is nothing but shift left. That means data will be shifted to the left side by 1 bit for 1 clock pulse. So as long as the number of clock pulses are applied, data will be shifted to the left side like this, and also data is rotating like this. Okay, shift left as well as rotate left. Shift left as well as rotate left. That's why ring counter will be doing the functions of both shifting the contents as well as rotating the contents to the left side. Ring counter will be doing the functions called as shifting the contents of the register as well as rotating the contents of the register. Shifting the contents will be done here, and rotating the contents will be done here by connecting the output of last flip flop again back to the first flip flop. Will be doing the operation of rotating the contents, and shifting the contents will be done by this function. Okay, so that's why ring counter will be doing the functions of both shifting the functions as well as shifting the contents of the register and rotating the contents of the register. So ring counter resembles a shift left register and rotate left register. Bits are shifted left and fed back again to the input. So as long as the clock pulses are applied, bits will be shifting to the left side, and also the last output of last flip flop will be given as input to the first flip flop. That means you are giving some feedback from output to the input side again. So when the clear input goes low, the initial output word is Q is equal to 0001. So initially the outputs Q3, Q2, Q1 and Q0 will be what? 0, 0, 0, 1, because these three outputs are cleared, and the output of first flip flop will be presetted. Preset means making the output of the flip flop to be 1 irrespective of the inputs and clock pulse applied, and clear input means making the output of the flip flop to be equal to 0 irrespective of the inputs available and clock input applied. So the Q3, Q2, Q1 flip flops will be cleared, and the first flip flop will be presetted, making the output to be equal to 1, and cleared means making the output to be equal to 0. So initially the outputs available will be 0, 0, 0, 1. And if you are applying the clock pulse once, what will happen, this 1 which is available at the input of first flip flop will be transferred to the 1 which is available at the input of the second flip flop will be transferred to the output. So after the application of first clock pulse, the output becomes 0010. So now earlier Q3, Q2, Q1, sorry, I'll write clearly, Q3, Q2, Q1 and Q0. Whenever no clock pulse is applied, initial contents will be 0001, and after the application of first clock pulse, this 1 will be shifted here. So and this 0 will be shifted here. So that is the operation of ring counter. Similarly, after the application of second clock pulse, this 1 will be shifted here, and this 0 will be shifted here, and this 0 will be shifted here. So 0 1 0 0. Similarly, after the application of third clock pulse, 1 0 0 0, and after the application of fourth clock pulse, again it becomes 0 0 0 1. So that means there are only 4 possible different outputs: 0 0 0 1, 0 0 1 0, 0 1 0 0, and then 1 0 0 0. And after this, again it is coming to the first position, that is 0 0 0. That means there are only 4 possible different output states. That means this a 4-bit ring counter will be counting only 4 clock pulses starting from 0 to 3 or 1 to 4, you can say. So a 4-bit ring counter will be counting only 4 number of clock pulses. 4-bit ring counter will be counting only 4 number of clock pulses. Okay, so after the first clock pulse, output will be 0010. After the second clock pulse, output will be 0100. After the third clock pulse, output will be 1000, and after the fourth clock pulse, output will be again 0001. So it is coming to its initial position, and as long as the clock pulses are being continuously applied, its output will be shifting like this. So ring counters are used for producing ring word for different for timing different operations that takes place in a computer. So these ring counters are mainly used for producing ring word for timing different operations that take place in a different computer. So this is the truth table of ring counter, or you can say state diagram of a ring counter. So initially, whenever no clock pulse is applied, the initial contents, the output contents will be 0001, and whenever first clock pulse is applied, this 1 will be shifted here, this 0 will be shifted here, this 0 will be shifted here, and this 0 will be shifted here. Okay, so 0010. Next, whenever the second clock pulse is applied, what will happen? This 1 will be shifted here, this 0 will be shifted here, this 0 will be shifted here, and this 0 will be shifted here. Okay, next, whenever third clock pulse is applied, this 1 will be shifted here, this 0 will be shifted here, this 0 will be shifted here, and this. Okay, whenever third clock pulse is applied, this 1 will be shifted here, and this 0 will be shifted here. Okay, so depending upon the number of flip-flops you are using, that many number of different output states will be possible for a ring counter. So for example, if you are considering a n-bit ring counter, will be having n output states, so that it can count only n clock pulses. It can count only n clock pulses. Okay, so that is the difference between ripple counter and ring counter. Ripple counter can have, for n bit ripple counter can count a maximum of 2 to the power of n number of clock pulses, whereas n bit ring counter will be counting only maximum of n number of clock pulses. Okay, so this is a simple state diagram of a 4-bit ring counter. And if you can also observe the timing diagram, see here I am applying negative edge triggering flip flop. I am considering negative edge triggering clock. These are the different negative going triggering edges triggering pulses I am applying to the each and every flip flop, so that initially the output will be 0 0 0 1. 0 0 0 1 is the outputs available at the outputs of each and every D flip flop before applying the first clock pulse. So after applying the first clock pulse, again the outputs will be 0 0 1 0. So this one will be shifted here, this 0 will be shifted here, this 0 will be shifted here, and this 0 will be available here. Similarly, after the application of second clock pulse, outputs will be 0 1 0 0. That means this 0 will be shifted here, this 1 will be shifted here, this 0 will be shifted here, and this 0 will be shifted here. Similarly, after the application of third clock pulse, it will be 1 0 0 0. This 1 will be shifted here, this 0 will be shifted here, this 0 will be shifted here, and again this 0 will be shifted here. And after the application of fourth clock pulse, again it will come back to its original position 0 0 0 1. Okay, again this 1 will be shifted here, 0 0 0 will be shifted like this. So depending upon if you keep on applying continuously the number of clock pulses, these four different output states will repeated number of times depending upon how many number of times you are applying the clock pulse to the ring counter. So this is something about the timing diagram of a ring counter, timing diagram for ring counter. Next we will move on to the applications of ring counter. Ring counter is mainly used in the digital computers to execute the instructions in proper sequence. We can use this ring counter, and in order to control the sequence of execution, we can use ring counter. These are the different applications of ring counter. Next we will move on to the applications of counters. Counters are mainly used as frequency dividers in digital clock, and counters are also used in parallel to serial data conversion. And also used for auto parking control applications we will be using, and also industrial digital control systems. So counters are mainly useful in industrial digital control systems. So one of the important application of counters is frequency dividers. One of the important applications of counters is frequency dividers, and these frequency dividers will be using in n number of ways in the various communication systems. For example, if you want to have a PLL like phase locked loop, in feedback path we'll be using frequency divider circuits. So there you need to have the output frequency to be divided by some integer part, so that is again fed back to the input of PLL. So there you need to consider the application of counters as frequency dividers. So overall summary, we have discussed about the ring counter and construction of ring counter, and working of ring counter, and also applications of ring counter. We'll move on to the quiz. A ring counter is a ripple counter, synchronous counter, circular shift register, none of the above. So the answer will be circular shift register, or also you can also say that ring counter is a synchronous counter as well as circular shift register, because ring counter will be the best example for synchronous counter, because in ring counter each and every all the flip flops will be applied with same clock pulse. All the flip flops are applied with same clock pulse simultaneously. So that is nothing but synchronous. So ring counter will be coming into the category of synchronous counter only. So both B and C answers are correct. Circular shift register is nothing but ring counter, and also ring counter is the best example for synchronous counter. So both the options B and C are correct, even though C is showing here, the options B and C are correct. Okay, for example, if you want to make this C answer only correct, then you need to write it here asynchronous counter. So ring counter is not at all an asynchronous counter, so in that case option C will be correct, circular shift register. Okay, next, frequently asked questions: explain the working of ring counter and list the applications of ring counters. So this completes the discussion of ring counter and its applications. Next, we will move on to the discussion of other topics. Okay, in continuation to the lecture, we will also discuss something about modulo n or modulo 3 or mod 10 counters. Okay, uh, okay. In general counters can be divided into two categories. Counters can be divided into two categories. One is binary and the other one is non-binary counters. One is binary counters and other one is non-binary. Binary in the sense which is the possible output states will be divisible by 2. Possible output states will be divisible by 2 and possible output states is not divisible by 2. That is non-binary. Okay, so for example, the example for binary counter will be mod 16, because 16 is, you can write that as 2 to the power of 4. Okay, whereas examples for non-binary will be mod 3, mod 5, mod 6, mod 7, mod 9. All these things will be coming into the category of non-binary, or mod 10 also will be coming into the category of non-binary counter, because you cannot write these numbers 3, 5, 6, 7, 9, 10, all those integers in the form of 2 to the powers, that's why all these counters will be coming into the category of non-binary, whereas the binary is nothing but mod 4, mod 8, mod 16, mod 32. All these will be coming into the category of binary counters. Okay, so this is the basic difference between binary counter and non-binary counter. So binary counter and non-binary counters are the two different types of counters which are based on the number of output states. If the number of output states can be write it as 2 to the powers, then that will be binary counters. If you cannot write the number of output states in the form of 2 to the powers, then that can be called as non-binary counters. Okay. So till now we have seen only what you can say binary counters, because in the previous lecture we have seen 4-bit triple counter which can able to count 16 different outputs. So 16 clock pulses, 16 is nothing but 2 to the power of 4. So 4-bit triple counter is a binary counter. Similarly, ring counter, 4-bit ring counter also counts 4 clock pulses. That's why 4-bit ring counter is a binary counter. So upon completion of this lecture, you will be able to know what is the working of modulo n counter and working of mod 3 counter and working of mod 10 triple counter. We will see all those things in the further slides. So first we will see modulo n counter, which you can also call it as divide by n counter. Modulo n counter, you can also call it as divide by n counter, and the modulus of the counter is the number of output states of that counter. Modulus of the counter is defined as the number of output states of that counter is defined as modulus of the counter. So for example, if I am writing mod 3 counter, that means there are 3 possible output states for that counter. There are three possible output states for that counter. So modulus of the counter is nothing but the number of output states of the counter is called modulus of the counter. So n stage counter will have maximum of 2 to the power of n number of different output states. So for example, if you are considering n stage counter wherein I am using n number of flip-flops for the construction of that counter, so that will be having a maximum of 2 to the power of n number of output states. That will be having a maximum of 2 to the power of n number of different output states. If a counter has to count n pulses, n clock pulses, which is not a power of 2. If a counter has to count capital N pulses, capital N clock pulses, which is not a power of 2, then we have to consider a divide by factor, which is same as the modulus. Then we have to consider a divide by factor, which is same as the modulus. So the counters which involves this factor are known as divide by n counters. The counters which involves this factor are known as divide by n counters. So divide n counters. To construct these counters, we have to start with a ripple counter of n flip-flops. To construct these divide by n counters, we have to start with a ripple counter of n flip-flops. As a count of n, at the count of n, all the flip-flops must be reset to 0. For example, if I want to construct a mod 3 counter, first you need to decide that how many number of flip-flops are required for constructing mod 3 counter. You need 2 flip-flops because 2 square is equal to 4 maximum output states will be, and 4 maximum output states will be possible, and out of that 4 you need to consider only 3 different output states. Okay, that means after getting 3 different output states, before getting fourth output, it has all the flip-flops needs to be resetted. If all the flip-flops are resetted before the fourth before getting the fourth output for the mod 3 counter, then you can able to achieve your goal. So that will become mod 3 counter. That means after getting 3 different output states, at the count of n, all the flip-flops must be reset to 0 by adding a feedback gate in the circuit. So by adding extra circuitry to the in addition to the flip-flop circuit, at the count of n, all the flip-flops must be resetted to 0, and by adding a feedback gate in the circuit, such feedback is provided by a NAND gate. In which the output provides all the clear inputs in parallel. So the flip-flop outputs of the counter are connected to the inputs of the NAND gate. So the flip-flop outputs of the counter are connected to the inputs of the NAND gate, so that we can able to achieve this divide by n counter. Or non-binary counter. So for constructing these divide by n counters, first we have to start with a ripple counter of n flip-flops, and after that, at the count of capital N number of clock pulses, all the flip-flops must be reset to 0, and this can be done by giving a feedback with the help of a NAND gate. So the flip-flop outputs of the counters are connected to the inputs of the NAND gate, so that the NAND gate output should be connected to clear input of all the flip-flops. So that all the flip-flops will be resetted. So this is how the procedure of constructing divide by n or modulo n, which is non-binary counter. Next we will mainly concentrate on mod 3 counter. So for the modulus 3 is not the power of 2. So two flip-flops are required to construct this counter. So with the help of two flip-flops you can have four different output states. Consider n, which should be smaller, for which 2 to the power of n greater than the, so n is equal to 2. So for n is equal to 2, this condition will be true. 2 square, which is nothing but 4, is greater than 3. So for, by using two flip-flops you can able to implement this mod 3 counter. By using two flip-flops you can able to implement this mod 3 counter. So this is the circuit diagram of mod 3 counter. We will see its operation step by step. Okay, so before applying any clock pulse, initially, let us say QA and QB are the two outputs. Let us say initially, before applying any clock pulse, let us say the outputs are 0 and 0. And see, since here I am using J and K flip-flops here, and all the inputs of J and K flip-flops are tied high, are applied to VCC. That means J and K flip-flop will be operated in toggle mode. And it is a ripple counter because the output of the first flip-flop is given as input to the second flip-flop. Okay, so let us say this is QB and this is QA. Okay, so output of the first flip-flop is given as input to the second flip-flop, so that this is not a synchronous counter, it is a asynchronous counter. So clock input is applied to only QA flip-flop. So whenever first clock pulse is applied, what will happen? The output of QA flip-flop will be toggled. So 0 becomes 1 and this 0 becomes only 0 only, because no clock pulse is applied to this. Okay, so the QB output will be changing only when QA output changes from logic 1 to logic 0. So here 0 to 1 it is changing, so you are not applying any clock pulse, so QB becomes 0. So after the application of second clock pulse, again QA toggles. So whenever QA is changing its state from logic 1 to logic 0, QB toggles. Okay, and this is the output. So this is the output at the after the application of second clock pulse. So whenever QB is becoming 1 and QA is becoming 0, what happens? Then the output of the NAND gate will be key. Then the output of the NAND gate will be high, and so that what happens? And after the application of third clock pulse, QB will not be toggled and QA toggles. So both 1 and 1 will be available. So when 1 and 1 are available at the outputs of JK flip-flops, so the output of NAND gate will become what? 0. So a low on this clear input makes zeros. So if the output is, as and when the output of the flip-flops become both ones, what happens? It will be overridden by this clear inputs. So that only 0 0 0 1 1 0, and then after that again it will start from 0 0. That means only 3 possible outputs are possible. So that means you are avoiding this 1 1 combination of output. With the help of this NAND gate. Okay, and in a similar manner you can also observe. So see, for clearing the inputs, the these clear outputs should be equal to zeros. So when clear output should be equal to zeros? When only QA and QB is equal to 1, then only output of NAND gate will be equal to 0. So when QA and QB is equal to 1, then the output of the NAND gate is 0, and that 0 is applied as clear inputs, so that J and K flip-flops, QA and QB flip-flops will be cleared. So instead of getting the outputs 1 and 1, now you will be getting the outputs 0 and 0. That means you are avoiding one of the output state as 1 1. So 1 1 output state is avoided. it is removed with the help of extra circuitry, that is NAND gate. Are you understanding? So that means the possible output states are what now? 0 0, 0 1, 1 0. And as and when 1 1 is, you are getting the 1 1 output, that will be overridden by the clear inputs. That will be overridden by the clear input. So only 3 possible output states are there. That's why this is the circuit diagram for mod 3. This is the circuit diagram for mod 3 counter. Okay, so this is the process of constructing mod n counter, where capital N is the number of outputs. Okay, so this is something about mod 3 counter. So this counter has to reset to 0 when the output reads 1 1. So as and when the third clock pulse is applied, so that the output reads 1 1, as and when 1 1 is available at the outputs QA and QB, which are given as inputs to the NAND gate, so that the NAND gate output becomes 0. So that 0 output of NAND gate makes clearing of the two flip-flops. Clearing of the two flip-flops. So this counter has to reset to 0 when the output reads 1 1. So hence the output of the two flip-flops are connected to the feedback NAND gate. Okay, so when the third clock pulse occurs, NAND gate gets the two inputs QA and QB as high, hence output of NAND gate is low, which resets all the flip-flops. When the third clock pulse occurs is applied, NAND gate gets the two inputs QA and QB as high, hence output of NAND gate is low, which resets all the flip-flops. So 1 1 combination, 1 1 output state is avoided with the help of the feedback NAND gate. With the help of the feedback NAND gate. So this is the timing diagram for mod 3 counter. If you observe, let us say I am applying the negative triggering clock pulses like this. So this is the first one, second, third, fourth, fifth, sixth, seventh, eighth clock pulses I am applying like this. So initially let us assume 0 0. Before applying the first clock pulse, the outputs are 0 0. And whenever the first clock pulse is applied, output becomes 0 1. Output becomes 0 1. And when the second clock pulse is applied, output becomes 1 0. When the second clock pulse is applied, output becomes 1 0. And when the third clock pulse is applied, one as and when outputs are becoming 1 and 1, as and when outputs are becoming 1 and 1, at that instant of time, QA and QB inputs, NAND gate inputs are QA and QB, both are 1s, so that NAND gate output becomes 0, so that making resetting of all the flip-flops. Resetting of all the flip-flops means making 0 at the outputs of flip-flops, irrespective of the inputs and clock pulse. Irrespective of the inputs and clock pulse. Again, when next clock pulse is applied, again the same operation, 0 1, and then fifth clock pulse. After the application of fifth clock pulse, output will be 1 0, and again after the sixth clock pulse, again output becomes the flip-flops will be resetted, making the outputs to be zeros, and then 0 1, and then 1 0. That continues. So total, if you observe, the possible different output states will be this: 0 0, 0 1, 1 0, 0 0, 0 0, 0 1, and 1 0. So these are the three different possible output states, so that this will be the timing diagram for mod 3 counter. This will be the timing diagram for mod 3 counter. Okay, so this is something about mod 3 counter. Next we will see what is mod 10 counter, and before that, if you observe, when the clear input is becoming high, when the clear input is becoming low, whenever QA and QB are becomes ones, whenever QA and QB are becoming ones at this small instant of time, there you are making clear input as 0. You are making clear input as 0, which resets all the flip-flops, which resets all the flip-flops. That is the advantage of clear input. Clear input is called as asynchronous input. Clear input is called as asynchronous input. So these asynchronous inputs are independent of the input applied to the flip-flop as well as clock input. Irrespective of the inputs available at the flip-flop and the clock pulse, if asynchronous inputs are activated, then flip-flop has to respond corresponding to that. Okay, so if clear asynchronous input is applied, then output of the flip-flop will be made to 0. Output flip-flop will be resetted. If preset asynchronous input is applied, then making the output of the flip-flop to be equal to 1. That means flip-flop will be setted. So that is the advantage of asynchronous inputs like clear and preset inputs. Okay, so that's it for the today's lecture. In the next lecture we will start discussing what is known as mod 10 ripple counter, which you can also call it as decade counter. So that we'll be discussing it in the next class. Thank you for listening.